good afternoon. Welcome back to another in a series of lectures for Chem 400. A couple of announcements. One is that your second exam is on Wednesday. You will have 90 minutes to do that exam, which means we will go from 12:30 by not back clock, but by cell phone time, all the way to 2 o'clock. So you have 90 minutes to do it. And then we'll on Wednesday continue discussion afterwards. So 90 minutes. Second thing is I graded what I think are all of your homeworks and your 2 take-home quizzes and all your discussions, I think, as well. So please do collect them. If you do not collect them today, I will put them in a box outside of my office door. That box will still be there when I'm not here. And note, the Calorimetry Quiz is very good review for your exam, so please take a look at it. Please take a look, especially if you made any mistakes. And you will note that I have posted an answer key for one of the calorimetry quizzes, again, for you to review in preparation for Wednesday's exam. Yes, I mean, I can't think of a problem that more exemplifies the material on the second exam. Any questions about the second exam or anything else about the class? One other announcement, Thursday morning to Sunday, I will be out of town and largely unavailable, so keep that in mind. Alicia, did you have a question or comment?
Both questions on the take-home quiz?
Both questions on the take-home quiz, yes. I mean, actually, when I look at the other take-home quiz, the one about the 2 bulbs, where the gases mix, also not a bad thing to understand and know for the exam as well. Beyond that, it's all such good stuff. No surprises. Nothing up my sleeve, even on the exam, except for the last question, which will be interesting to say the least. Any other questions? If not, then let's pick up where we left off. Where we left off was we had just a teeny tiny bit of Chapter 8 left. Chapter 8, Electron Affinity, the energy associated with the gaining of an electron by an atom or ion in the gaseous state. I will show you the reaction and energy for the first electron affinity of chlorine. If you remember last time, we were talking about what's called the ionization energy. And the ionization energy took an atom or ion and had an electron leave. Electron affinity, affinity means likes, so an electron liking thing. You're going to take the chlorine gas plus an electron and make another gaseous species, this one negatively charged. So the difference between electron affinity and an ionization energy is which side the electron's on, and of course, what the charged species is that you're creating. If you add an electron, it'll be negative. I also said I'd tell you the energy associated with this, the energy, which I will call delta H E sub EA1 for electron affinity 1, is negative 349 kilojoules per mole. What that means is that if you take a chlorine atom and you add an electron to it to create a chlorine gas ion, that species is lower in energy. Now, if we were to do an electron configuration for a Cl-, what element would it have the same electrons as?
Argon.
It would have the same electrons as argon. And so using a noble gas core, which we could do, it would have argon. And before that, it would be neon. (3s2, 3p5). Now, a couple things about this. So first off, all of the ionization energies that we saw or will see are positive because adding an electron to an atom is always an endothermic process. It takes energy to do it. What's unusual is that this is negative. And the reason it's negative is, again, due to the stability of having a noble gas set of electrons. The stability lowers the energy and makes this an exothermic process. Alicia, question?
What does the I stand for?
EA1. It's a 1. Now it's got serifs, but before it did not. So, why is delta H EA1 negative for chlorine? Because it is going to a noble gas core, which is low in energy. And we will never be able to prove this by itself, but we will see a number of cases where when you go to a noble gas core, it is low energy, and so you tend to give off energy when it's created. Last week what we saw was that when you break up a noble gas core, it takes lots of energy. Again, that means that noble gas cores are relatively low. Any questions about that? Okay. Third, so not a definition, electronegativity, the ability of a covalently bonded atom to attract bonding electrons. What I'll do in a minute is, at least for electronegativity and also actually for metallic character, I'm defining these even though we haven't even really done any Lewis structures yet. Those are coming up next. Electronegativity, huge when we talking about Lewis structures. Metallic character, what does that mean? Definition, working definition is good conductors of heat and electricity, malleable, ductile, and shiny when not covered by metal oxides. These are just definitions. It's good to be familiar with them, but what we really are going to be talking about is on the next slide. There we go. We define those because according to the shape of the periodic table, we will have 4 trends. All of those trends follow the shape of the periodic table, meaning these things will change as we go to the left and down. What we've seen is that as you go to the left and down, atomic size increases. And by atomic size, sometimes I use the word atomic size, and sometimes I use the words atomic radius, but those are really the same. Ionization energy. Decreases. And I'll throw the other 2 in there. Electronegativity, as you follow these 2 arrows, and I guess I could even make them connect so you know the trend goes all the way down. Electronegativity decreases. And metallic character increases. And in my understanding, these trends tend to go together. Once you understand the trend in atomic size, the way I understand it is as atomic size increases, the electrons get farther away from the nucleus, which means they are less tightly held and easier to remove. So ionization energy decreases because it takes less energy to remove an electron. Electronegativity, well, again, we'll talk more about this, but as the electrons get farther and farther away, it is related to the fact that the atom is less able to pull all electrons, including bonding electrons, towards itself, which is electronegativity. And now this thing called metallic character. So it is true what I am saying is the best metals in the periodic table are down here. The worst metals, also called nonmetals, are up here in the top right portion of the periodic table. So maybe that's one way to remember it. But what I'm saying too is, as you go over here, as you get down to cesium and barium, their electrons are so lightly held that they move really easily. That's conductivity. Conductivity is the ability to move electrons. Now, maybe your question is, well, if the best conductors, the best metals are cesium and barium, why don't we have wires made out of cesium and barium? Does anybody know? It turns out they react relatively explosively when exposed to water. And since there's water vapor, if you wanted wires that were really conductive but then ate themselves or reacted away, then maybe you'd use them. And it turns out that copper, silver, gold, aluminum, the metals right around iron, steel is made out of iron and some other elements. Those are not the best conductors. Those are the best conductors that don't react away over time. Although iron rusts, actually, so you don't see too many wires made out of, electronics wires made out of iron. But copper, great conductor, used in all kinds of wiring, aluminum as well. Why? They're stable and they're relatively good conductors. So I think Alicia and then Bodhi, do you have a question?
Why are gold and silver so special?
Why are gold and silver so special?
Not reactive.
Good question. So why are they non-reactive? That is a good question. Off the top of my head, I don't. So I know so those are the ones that have the 3D, 4D, 5D, 10. I don't actually. That's a great question. I don't know the answer to them. I know they are. And the other thing that makes them special is they're relatively rare, and when you polish them, they look nice and shiny, and so people want them. They're worth money to other people, whatever money is. Little pieces of paper. Bodhi?
Aluminum conducts electricity?
Aluminum conducts electricity well, yes.
But it's not magnetic. Magnet doesn't stick to it.
But it cannot be made magnetic, that's true. No, and in fact, we did talk about, just an aside here, we did talk about paramagnetic versus diamagnetic. There is a third thing, that's ferromagnetic. Ferromagnetic means can be permanently magnetized. It turns out the qualities that you need for those are all right around iron. You need to have lots of unpaired electrons, which those elements do, and you need to be relatively small. Put those two combinations of properties together, and those are, it turns out, why magnets are made out of iron, cobalt, maybe some portion of nickel as well, that region. Bodhi?
So what happens when a magnet sticks to something? Like what electron wise?
So what happens, I guess maybe, let me see if I can rephrase and then we'll go from there. Why does something become magnetic? It turns out that all those little tiny spins that are unpaired you heat it up, you apply a magnetic field, those spins align, and you cool it down and they stay relatively well aligned. Now what does that mean? Maybe 10% more of them are aligned in this direction than randomly, but that's enough to make it permanently magnetic. What happens when a magnet is attached to another magnet? That's a good question as well. I'm not sure if I could do that justice. Certainly nowhere near as good as a physics professor could. And I know there's attraction between opposite. Yeah, no, I'm lost actually.
Is it because of intermolecular forces, or is there sharing electrons?
It is not chemistry. It is not intermolecular forces. It is magnetic fields. It is a different. It's like gravity is different than intermolecular forces. The magnetic forces as well. It's all related to positions of charges, but I'd have to think about it way more than I think I can right now. These are good questions, and what I would suggest is, and this happens to me all the time, as you're, like, I'm really happy that you're coming up with questions that I cannot answer, because I think it means you're engaged, and I appreciate that. So, and Chem 400, you will come up, I mean, and you could probably Google it, and somebody out there has already done it. Not right now. I appreciate you still paying attention. But no, there's so much stuff out there that is so interesting. Oftentimes when I'm cooking, I think of new research projects for my undergrads. So that's just what I think. Metallic character is a couple things. It's movement of electrons, which is conductivity. It's movement of heat. It's malleability and things like that. Those are all related to the properties of metals, which we may or may not get to talk about much more. All you need to know for Wednesday's exam and throughout the next few chapters is these terms. Any other questions?
I'm a little confused about the question in homework about the sizes of diameters, because I know that how an individual cation compares to its, what's the word, to its counterparts, how those two compare, or an ion compares in radius to its counterparts, but not how they stack against each other on the, that was kind of confusing. They may have the same number of electrons, but they have different masses of protons. I don't know how to answer that question in homework.
Well, so this is a good topic for the exam, so let's take a minute to review, or a couple minutes. So certainly this is just atoms. And atoms get bigger as you go this way, and bigger as you get this way. And on the homework, I think this is a homework. I've been looking at some of the old exams today too, but as you go down a period, n increases, and the larger n is, the larger the atoms. The way I think of the size is actually when it decreases going this way, and it decreases because there are more protons pulling the electrons closer to the nucleus in the same value of them. So those are the atom sizes, and those are great topics for Wednesday's exam. The other questions I can ask you are about what's called an isoelectronic series. And the key for isoelectronic series is more protons equals smaller. And I could further say, although I think it already says it, isoelectronic, we're specifically talking about comparing species with the same number of electrons. So more protons equals smaller for the same electrons. Other questions I can ask you is, what happens as you add an electron? As you add an electron, atoms get bigger when they become ions. As you subtract electrons, atoms, or this ion will be smaller. So, and again, this now has the same number of protons. So, Leo?
I have a question about isoelectronic series.
Yes.
So if you had a calcium atom and a Ti2+, a titanium 2+ ion, they would have the same electrons, but they would not be in the same orbitals. Would that count as an isoelectronic series?
That is a good question. All right, so calcium atom, argon, 4s2, argon, 3d2. Which one would you think would be smaller or bigger?
Titanium is smaller.
Titanium is smaller because two things. One is, first off, in this case, 3D is typically going to be smaller anyway than 4s. Second, two more protons. I mean, that seals the deal. So, but although, and it's a very good question, we could answer that one. Sometimes you'll get to a case, though, where it's not clear, and you'll be like, well, I think this is it, and then you go look it up. But in this case, I think we got it.
Okay.
Good question. Alicia, does that address your question about trends, more or less? Let's see, is that the last slide in chapter 8? 30. Done. All right. So we'll start chapter 9. All right. Chapter 9, finally, chemical bonding. Chemical bonding involves each atom gaining, losing, or sharing electrons to get the same valence electrons as the nearest noble gas. This is called the Octet Rule, because noble gases, except for helium, have 8 valence electrons. We've seen some examples of why noble gas sets of electrons are lower in energy. We're not going to see anything new about that moving forward. We just now understand that noble gases, that's what all the atoms balance. Lewis dot formulas, we have a page for this. Display the valence electrons as dots around the chemical symbol. We've talked about valence electrons before. I'm going to do, for the chlorine atom, the entire electron configuration. For chlorine, there are 17 electrons. I'll do the whole thing this time. 1s2, 2s2, 2p6, 3s2, 3p5. Whoa. Still up on the other slide with the noble gas cord. Reminding you what valence electrons are. They are all the electrons with the highest value of n. I find my highest value of n here. I have 7 valence electrons. The Lewis dot formula will be the chemical symbol Cl with 7 dots around it. I actually don't care how you do the dots, but typically how it's done is in pairs. What we said before is that the number of valence electrons, you can look at the column heading on the periodic table to get an idea. For example, chlorine is in group 17. It has 7 valence electrons. It's always the single digits place that tells us. Oxygen, sulfur, selenium have 6 valence electrons, nitrogen, phosphorus, arsenic, 5, etc. According to that, sodium will have 1 valence electron, and that will be the 3s1. Any questions about this? An ionic bond is defined as the attraction between oppositely charged ions, cations and anions. Of course, cations are positive, anions are negative, in large numbers to form a solid called an ionic solid. One way of understanding how this process works is you take 2 sodiums and 2 chlorines and you get sodium chloride solid. Shay, question?
Yeah, so would that be based on the electron configuration up there? So if we did the abbreviated electron configuration, if we just took the things after the noble gas, would those be considered the valence?
Good question. Oftentimes, yes. However, the thing to be aware of is when you get into the transition metals, you'll have, depending upon how you do it, so let's do nickel. If you did the nickel atom, you would see 4s2 and 3d8. Only the 4s2 electrons are valence electrons, though.
Okay.
All right, so that's why the thing I remember is look for the highest value of n. The other thing we know about that is for the highest value of n, those are the electrons that are farthest out from the nucleus. Is another one. Did that answer your question?
Yeah.
Yes. So what you can show here is if you start with sodium atoms and go to sodium plus. To become sodium plus, it loses 1 electron. Has the same electron configuration as neon. However you do it, and hopefully you draw an actual R there. Chlorine has the same 18 electrons as argon. Both of the atoms get noble gas cores. Then the actual ionic bond is the attraction of those 2. Similarly for lithium oxide. Good. There's not a whole lot to ionic bonds as far as bonding goes because we're familiar with the atoms, we're familiar with the ions, at least in general. I think the one thing to keep in mind is even when you have a noble gas core, the number of valence electrons is 8. If we look at sodium and then the neon electron configuration, sure enough, there are 8 valence electrons in there. I don't know, I think most students are okay. Significantly more complicated are covalent bonds. A covalent bond, co means shared, valent, valence electrons when 2 atoms share 1 or more pair of electrons. Those are almost always valence electrons, so hence the name covalent bond. Generally occurs between 2 nonmetals. So we are in the upper right portion of the periodic table almost exclusively when we're talking about covalent bonds. It turns out that that works very well for Chem 400 and Chem 401, although that is one of those things that gets relaxed as you move on to other classes and farther into your chemistry careers. What we will see is that another definition of a covalent bond is a bond for which the difference in electronegativity is greater than or equal to 2. Greater than or equal to 2. Wait a minute, sorry. Less than 2. I had to put my own alligator in the wrong direction. Less than. It is less than. It's not less than. And what I'll do is, for difference in electronegativity, delta means difference or change. Difference in this case, E, capital N is difference in electronegativity. What I have here is a picture of the energy versus distance of separation between two hydrogen atoms. And it actually says internuclear distance here. That's true. That's another way. That's actually what this is. But you can think of it as distance of separation. What happens is, for the formation of a covalent bond, we can imagine a hydrogen atom, which will have a Lewis dot formula of H dot. That's one valence electron. Plus another hydrogen atom goes to H2, in which these two electrons are shared and will be represented by a dash. A dash is a covalent. What we're getting at right here is, way out here you have two hydrogen atoms. Very far apart, and there's no attraction between them. As you bring the two hydrogen atoms together, there is an attraction. When that attraction hits a minimum, that is the bond length. So bonds form because the atoms in them lower their energy by forming the bonds. And that creates a bond length. And that's what we're doing now. So a covalent bond forms. Because the two bonded atoms lower their energy. Which goes along with many of the things we've already said. Once these two atoms get to their minimum energy, in order to break the bonds, you've got to, in order to move farther apart or even closer together, it gets higher in energy, so that tends to, like a ball in a slight depression here, it tends to keep it at that minimum energy. Unless you get this much energy added to it, and you have enough to break them apart. Any questions about this so far? All right. Now, really these atoms are attracted to each other because the electrons of one atom are attracted to the nucleus of the other. The electrons of the other atom are attracted to the other nucleus as well. That's what gives rise to this lower energy. However, if you get extremely close, then the nuclei start being repelled by each other, and that's what we're seeing in here. So what is a covalent bond?
Two non-metal.
It does involve two nonmetals. I'm going to suggest to you that a working definition, or a useful definition to remember, is a covalent bond is when two atoms have a lower energy because the shared electrons are attracted to both nuclei. Because the shared electrons are attracted to both nuclei. Now, this picture right here is not so different than something we've already done. We've drawn what's called a reaction energy diagram. A reaction energy diagram has potential energy on the y-axis, reaction progress. On the x-axis, it has reactants and then products. I'm going to put my two reactants here, which are two hydrogen atoms. And my bonded hydrogen molecule down here. Can anybody tell me what this difference in energy is called? Delta H reaction. And this is very exothermic. The two atoms are lowering their energy by forming. Okay. So that's a little background. Question?
Yeah, I don't know if it's a good question or not, but how do electron orbitals change when bond atoms?
Good question. That is a good question. How do orbitals, or sorry, did you say atomic or electron orbitals change when there's bonding that occurs? The short answer is, I'm about to tell you a procedure for making a Lewis structure that will tell you nothing about that. All it will say is, everybody wants 8 electrons, make it happen. And here are a nice set of rules for making it happen. And those set of rules will work greater than 95% of the time. But if you want to understand orbitals, you have to deal with orbitals that are called molecular orbitals. And we will, but not yet. And molecular orbitals will be so complicated and 100% correct, but require advanced calculus if you want to do molecules that have any more than 2 atoms, which for us will be largely useless because all of the biology and most of the chemistry molecules have more than 2 atoms. So there is a way to describe the orbitals of molecules exactly. We won't get to it, largely. We'll do a taste of it.
And for 100, or like, what did you get it for 1, or is that like an organic chemistry?
You'll touch more on it in organic chemistry, but still not too much. To get to what happens to an orbital during bonding, you really got to get to junior and senior level chemistry, which mostly chemists are the only ones who take it. All right. Yes, I was going to move on. All right. So it's a good question, but no, there's too complicated for us. And, I mean, too complicated and not useful, right? I would say, I mean, if you want to do If you want to understand reactivity and things like that, then yeah, you're going to have to go there. But again, most of what we talk about is just accepting that reactions happen. So now we're ready to do Lewis structures, and there are a number of ways to do Lewis structures. I'm going to show you my way. I can handle, again, all of your ways and work with you in whatever way you want to. But here's mine. So start with the octet rule. Everybody wants 8 electrons. The two obvious exceptions, helium and also hydrogen. Hydrogen is a non-metal. It has 1 electron. It only wants the electrons of helium. So it wants 2 electrons to share. Now I'm going to take you through my steps for drawing, for writing a Lewis structure. My example will be carbonate ion. Determine the total number of valence electrons. Carbon, looking at the periodic table, can anybody tell me how many valence electrons an atom of carbon has?
4.
It has 4. How about an atom, one of them, of oxygen? 6. There's 3 of them, so I have 3 times that 6 number. And now I have a 2 minus charge. When I have a 2 minus charge, do I have to add or subtract 2 electrons? We must add. And so I put plus 2 electrons for charge there. Again, just whatever your process is, add them up. There are 24 electrons. They are, 22 of them are valence electrons, but because of the charge, the 2 extra electrons were kicking in there, I'm just going to call them electrons. And the way I do Lewis structures, there are 24 electrons for the whole molecule. I do not associate them with any particular atoms now that I've collected them. So I'm going to write 24 electrons for the molecule, or well, let's say it's for the Lewis structure. Here comes electronegativity. Our trend from chapter 8 says as you go to the left and as you go down, your electronegativity decreases. Between carbon and oxygen, we're going to place the least electronegative atom, except of course hydrogen, as the central atom. What that looks like is put the carbon in the middle and surround it by the other atoms. You'll never put hydrogen in the middle. It has 1 valence electrons. It wants 1 more, and so we will briefly note that it only ever forms 1 bond. You cannot be in the middle of anything if you only form 1 bond. Connect atoms by single bond. Each bond is 2 shared electrons. Each bond is a dash. And so when I come back and add a step 3 here, it will look like that. Step 4, this is not a very technical term, but it is how I do it. Sprinkle remaining valence electrons around the outside atoms first to complete octets. Then last, place any remaining electrons on the central atom. I will sprinkle my electrons now. I also keep track of them too. I'll go 2, 4, 6, 8, 10, 12. That oxygen has an octet. I'm done. 14, 16, 18. Done. 20, 22, 24. Now, can I put any more electrons in there now that I've gotten to 24? No. So many of you will be tempted by the dark side, to put electrons right there, because you want octets. But you cannot, like, it's always 2 points for any exam, just having the right number of electrons, valence electrons and charge electrons, in your Lewis structure. If you do not, -2 right away. So make sure that is true. That is the end of step 4, and so step 4 is in red so far. Now, we make double or triple bonds as needed to complete octets. What I'm going to do is I'm going to rewrite step 4 over here and then do the double bond making. So that's where we are after step 4. Step 5 is going to notice that carbon does not have an octet. Therefore, I will move one pair of electrons in here to make a double bond. Like so. And it doesn't matter which oxygen you pick, as long as you pick one, and as long as everybody, in the end, everybody meaning every single atom, has an octet. Finally, if it's an ion, place square brackets. And add the charge. This 2 minus means that there are 2 extra electrons in here. And we want to make sure we acknowledge that fact, because CO3 with no charge versus CO3 with a 2 minus charge are entirely separate species and will have entirely different Lewis structures. Questions about this? How many people have made Lewis structures before? All right, well, but still, this is chapter 9. We cover everything, as my colleague Bruce Zenner would say, from soup to nuts. My note for this one, I'm going to have a little table here with some elements, and I'm going to have over here typical. Typical number of bonds. I mean, really, there's 4 elements we almost always use when we do these. Carbon, hydrogen, oxygen, nitrogen. Typical number of bonds for carbon, 4. Look at that, carbon, 1, 2, 3, 4. Pretty typical. Few exceptions, but not too many. Hydrogen, 1. Except for hydrogen, instead of typical, I will write always in all caps, as if I'm yelling it at you, but I'm not. Oxygen typically has 2, but based on the Lewis structure for carbonate, is that rule already broken? Are there oxygens with 1 bond? Yes. So that's one's broken pretty often. Nitrogen typically 3. And but I will say, I mean, typical, yes, but these are we will see many examples in which there are other things going on. All right, that's the only note I have for that. Now let's do what's called formal charge. How many people in their Chem 300 or elsewhere have done formal charge before? Raise your hand. Okay, a couple of you, but not that many. So this is where things get new. Formal charge, Fc, is my abbreviation, capital F, capital C. It's going to equal, and what I'll write in these brackets is number of valence electrons from periodic table PET is an abbreviation for periodic table. Minus two different things, which both of them will be minus, so I'll use the square bracket. Number of bonds. Number of lone electrons, or individual electrons. And I'm going to show you what that means right now. I will redraw the Lewis structure for carbonate. There's the bonds. All Lewis structures have all electrons on them. All Lewis structures have all electrons on them. I write that because at some point we'll start doing shape, and when you draw shapes, you don't have to draw all the electrons, but all Lewis structures have to have electrons. All right, so we're not quite done here. Now my Lewis structure is done. Now I can start talking about formal charge. I'll do formal charge in red. And I'll do formal charge on carbon first. This portion does not have any of the higher math. It's all adding and subtracting. Formal charge on carbon, number of valence electrons from periodic table. We've said that's 4. Looking at this central carbon atom, number of bonds, 1, 2, 3, 4 bonds. Number of individual electrons, that means these little dots, 0. The formal charge in that carbon is 0. I know. All right. Now you'll note that there are 2 oxygens with 1 bond and 1 oxygen with 2 bonds. I'm going to call these oxygen A, the ones with 1 bond. Formal charge on oxygen A. Number of valence electrons from periodic table. 6. Minus number of bonds. 1. And 1, 2, 3, 4, 5, 6. Yep, that's the same. 1, 2, 3, 4, 5, 6. 6 minus 7, -1. Bodie, question?
Is the number of individual electron pairs?
No, that's the tricky part. Individual electrons. Number of individual electrons. Counting one at a time. It wouldn't color code well, but you could write count one at a time. And what we'll do, good news, we'll do this 50 to 100 times over the next couple of weeks, and it'll be like, yes, we will be used to counting them one at a time. Formal charge on oxygen B. Well, for oxygen B, still 6 valence electrons. For oxygen, it is oxygen after all. Two bonds for this oxygen plus 4 individual electrons equals 0. And what this allows us to do is instead of just having the 2 minus for the entire Lewis structure, it will allow us to identify where those negative charges are. We can see that each of the oxygen A's has a -1 formal charge. Shay, question?
Yeah, why do we still have 6 valence electrons on the oxygen B?
Like when I use this number here? That is because it is from the periodic table.
Oh.
Right? So that it's like, and so really this calculation compares the number of electrons around it in this interesting way to the number that it had before it bonded. That's the idea. And any electron that is all on the atom gets counted fully, and you get 1 of the 2 electrons for the bond. That's why it's just number of bonds there. So, final step is to note the formal charges on the Lewis structure. I'll do that in blue. We now know that each oxygen A has a negative formal charge, and it doesn't matter where you put it, as long as you can tell it's associated with this O. I like to put them sort of far away. So down there is fine, down here is fine. Where the A is also fine, as long as you can tell that negative formal charge is associated with that O. And by convention, formal charges are placed in circles. So that is no accident that it's in a circle, and I will expect you to do that. Some things we get away with. There's a negative formal charge there as well. And from now and forever henceforth, all Lewis structures will have formal charges on them, because we're interested in where those charges are. This oxygen B had no formal charge, so there's nothing around it. Same thing with the carbon. And so what this does is it says, according to formal charge, where are those 2 negatives? We would say associated with each of these oxygens. Good. Let's see. Rules for writing the best Lewis structure. Okay, because all Lewis structures will do what's called a formal charge analysis. My abbreviation for Lewis structure is capital L, capital S. All Lewis structures require a formal charge analysis. What that means is that you'll make your Lewis structure, you'll find any formal charges in it, and you'll label them as such. And that's how you find the best Lewis structure, and I will show you what that means. 1, the most likely Lewis structure, or the best Lewis structure, has the fewest atoms with non-zero formal charges. Negative formal charges are more likely to be on more electronegative elements. Example, write the best Lewis structure for SCN. SCN, of those elements, well, let's count up our valence electrons. Because you always go back and make a Lewis structure, then do the analysis. Sulfur has 6 valence electrons. Carbon has 4. Nitrogen has 5. Plus 1 electron for the negative charge. Add that up, that's 16 electrons. If you go back to the rules say take and put the least electronegative element in the center. That turns out to be carbon. There's our bases. Questions so far? Sprinkle electrons, starting with the outside atoms. I have 2, I have 4, 6, 8, 10, 12, 14, 16. I can't put any more up because I'm out. Right? Now I have to form double and or triple bonds. What do you think I should do? 2 doubles, triple, single, single, triple. It's like we're talking baseball here, but baseball season's over.
Single triple.
Single, triple?
Triple on the nitrogen.
Well, let's see. So we have one suggestion. We have, where's the triple go in this one? On nitrogen side? Now, let's compare these two anyway. If this is a double bond, it's because I moved 2 of the electrons from sulfur over. Same thing for nitrogen. I didn't do anything to this sulfur, but then I moved 2 pairs from the nitrogen, and therefore there's only 1 pair of atoms. Now we'll do a formal charge analysis to see which one of these is the best. The best one has the fewest number of atoms with non-zero formal charges. Let's look at this carbon. What's the formal charge on the carbon in either case? 0. 4, and this almost always happens, 4 electrons from the periodic table, 4 bonds, done. 0 formal charge. But now, we'll call this, let's see. Let's do this sulfur. For this sulfur, we have 6 valence electrons from the periodic table. Minus 2 bonds, minus 4 individual electrons. What do you get when we do the formal charge on nitrogen? It is -1. That's 5 electrons from the periodic table. I have 2 bonds, 4 lone electrons. That is -1. And I put my minus circled by my nitrogen. If I do the other case, I will get a negative formal charge on my sulfur. Both of these will have 0 formal charges. It is always true that the charge on the ion always equals the sum of the formal charges. And that's a useful check for if you're doing your formal charges correctly, and if you should look for more formal charges sometimes. There's actually a third case, by the way, and you can think of that in the privacy of your own home. It would be sulfur, triple bond carbon, single bond nitrogen. But now let's refer to these rules. The best or most likely Lewis structure has the fewest atoms with non-zero formal charges. Okay, they're equal in that way. Negative formal charges are more likely to be on more electronegative elements. Well, nitrogen or sulfur, which is more electronegative? Interestingly enough, by looking at the periodic table, we cannot tell. If we start at oxygen, we know that the trend is electronegativity decreases this way, electronegativity decreases that way. They're catty corner to each other. And that is why on your third exam, you have a table of actual values of electronegativity, so you can tell them apart if you look it up. Electronegativity for nitrogen is 3.0, electronegativity for sulfur 2.8. And therefore, nitrogen is the more electronegative element. This is your Bacillus structure.
Do you ever expect us to memorize any of the electronegativity charges or just trends?
Good question. Do you have to memorize electronegativities? No, just the trends. So if I had carbon and nitrogen and said which one's less electronegative, you would have to tell me carbon. But for something like nitrogen, sulfur, carbon, phosphorus, no, you don't. Like, I will give you those values. And in fact, that's why I give those. All right, if we look at this case, we're going to have plus, and -2. Très terrible. 2 formal charges, plus or -2, still adds up to -1, by the way. Still true here. There is no prize for last, but this is the worst one we could think of. Okay, any questions about this? So, next slide. Is blank. And that's blank so that I could do my own thing here. How about we do nitrate? Lewis structure for nitrate. Nitrate. Same process, always the same, ad nauseum. Add up the number of valence electrons, add electrons or subtract them for charge. Put the least electronegative atom in the center. That would be nitrogen. Sprinkle electrons while counting them. 2, 4, 6, 8, 10, 12. You know what I like to do sometimes when they have octets? I like to make little smiley faces in them. As long as it's not too confusing because there are more dots. Here, how about that? It's just a smiley face. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23. We're done with putting in electrons. We still have an atom that does not have an octet. This looks very familiar, by the way. because we just made the carbonate ion, and now we're going to take one of these pairs, move it over. Still happy, by the way. Now our bonding pattern has a double bond to the left, although it could be the right, could be whichever oxygen you want. Put all the electrons back. Now, before you had to have square brackets in the charge. Another option is just to show formal charge. You have to show the charges somewhere. It doesn't matter where they are. I'm going to do it here. We have, again, well, the oxygens we've done before. You can see that oxygen with 2 bonds and 4, that will have 0 formal charge. -1. -1. And we're not done yet. I will say this. The formal charges have to add up to the charge. The charge on the thing is -1. So far we've got -2. So we better go looking for a positive formal charge. Does nitrogen have a positive formal charge? Yes, it does. Because it has 5 valence electrons and only 4 bonds and nothing else. Put the plus next to nitrogen. It's a lot of formal charge. But everybody has octets, and that's how it is. That's just the way it is. Any questions about this? Anybody want to see me do any of the formal charge calculations for this? Bodhi? Nitrogen. Formal charge on nitrogen. We have 5 valence electrons from the periodic table. It's like the third exam, I feel like a lot more people look up there. Because, at least I do. Then we're subtracting number of bonds, which is 4. Plus number of individual electrons around the nitrogen, which is 0. 5 minus 4 plus 1. Good. Questions about this? Good. Okay. So we'll do a lot of those. I feel like we've already done a bunch. So, all right, so you do your Lewis structure, and the rest of the course is built around doing Lewis structures. Let's be honest. You're going to do 100 of them, right? More in the next 5 weeks than you've done limiting reactant problems the entire semester. It's going to be intense. But that's what everything is about right now, is Lewis structures, and then take the Lewis structure and analyze it 4 ways to Sunday. Maybe even 5. So you always do the Lewis structure. Then you always do formal charge analysis. And then you always make the best Lewis structure. And we've got a couple things to make our Lewis structures even better. Exceptions to the Octet Rule, that's where we start. Beryllium only wants 4 electrons and 2 bonds. Why? Because it does. And you don't have to memorize that. I'm putting it in parentheses, which means we'll actually see it, because some examples that we use on future lectures use beryllium because they're just perfect. And you'll see that we'll only have 2 bonds, and it'll look something like this. Beryllium chloride. Beryllium only has 4, small enough that it can break the rules. Boron only wants 3 bonds. Well, let's say this only wants 6 electrons and 3 bonds. Classic example when we talk about electron geometry is going to be boron trifluoride. My recommendation is if you ever need to answer a question about boron or beryllium, and this one gets the parentheses too, you look it up. Just know that. So, I mean, I just drew covalent bonds for things that are near the top of the periodic table all the way to the left and they're not hydrogen. Weird stuff is going on. Stranger things. Odd numbers of valence electrons. Well, I don't know if you've noticed, but every single Lewis structure we've done so far, and every one you will do, has an even pair of valence electrons. If you find an odd number of valence electrons on a problem on my exam or my homework, and it doesn't say these will contain odd numbers of electrons, then recount. It's like getting 100,000 moles as an answer. You never know what I'm going to pull, but probably not. So double check. Right? Odd numbers of electrons, double check. It's easy to forget the electron for charge. All right, but odd numbers of valence electrons. The example is going to be NO. That is an example, not an answer. NO turns out to be pretty stable. By stable, what I mean is it exists. It is a pollutant that comes out of the back of your cars. My car, too. I guess if you have an electric vehicle, it doesn't. So if you have an electric vehicle, this does not come out. But when you have an electric vehicle, what you do is you plug your car in, and the place that pollutes is way over there where they make the electricity. So the NO, the nitrogen monoxide, comes out over there. 5 plus 6, there are 11 valence electrons. We draw them together with a bond. There is no central atom when there's only 2. So sprinkle. I like to sprinkle with my more electronegative atom first. 2, 4, 6, 8, 10, 11. For odd numbers of valence electrons, it will be impossible to get everybody having 8. So don't go over for nitrogen or oxygen. So my final answer, and I'll draw it over here. Nitrogen will only have 7. This is a perfect example of Lewis structures fail. I said they only work 95% of the time. That 5% includes things with odd numbers of electrons and not being able to predict them existing. But molecular orbital theory with 2 atoms, which is 100% correct, but almost always requires advanced calculus, will say, yes, this is stable. Yes, this should be coming out of your tailpipes if you burn fossil fuels. Anyway, enough about odd numbers of valence electrons. I will square this, and you may see this case, but it will be advertised as look for odd numbers of valence electrons. Now this is the big exception you have to know. And I think it best if we just start there next time so that it's after your exam. Our next lecture after today is not Wednesday because that's an exam. It's not next Monday because that's a holiday. Veterans Day, through which we do and should and do honor our veterans. It will be 9 days from now. We'll stop there. Cody, question?
Nah.